video for assignment 6 for ProbStats. All your assignment is to watch this video. I'm going to try to explain. This is one of those things that would take me more than a class to explain. So I'm going to try to explain most of it. Then we'll go over more of it on the next video, and I'll probably put that out like tomorrow or sometime. And then we'll do an assignment over this section. This deals with measures of regression. That's what we've been dealing with, and prediction intervals. What we're going to do, interpret the 3 types of variation. There's 3 different types. We're going to talk about those. Find and interpret the coefficient of determination. That's the R squared. We already talked a little bit about that. So we're going to do some more with that. Find and interpret the standard error of the estimate of a regression line. And that's all that's saying is we got our regression line drawn in our graph. We're trying to figure out what causes a point to be here when we would predict that that point should have been there using our regression line. Construct and interpret a prediction interval for your Y. So when we're predicting the Y's, we're going to construct an interval and say, okay, we're pretty sure, or 95% sure, whatever, that Y is going to fall in this range if we predict it off of our line, off our regression line. 3 types of variation about the regression line. It says line underneath this right here. So the 3 types of variation are total variation, explained variation, and unexplained variation. To find the total variation, we got to first calculate the total deviation, the explained deviation, and the unexplained deviation. So we got to figure out these 3 things before we can find these 3. So all the deviations talk about is how our Y's deviate off of our regression line, how they differ from what we would predict using our regression line. These are just some key things here that we need to know what they mean. Whenever you see this point, that's your X sub I and your Y sub I. These are your original data points. So these are the data points that are given to you in the problem, or the data points that you collected if you were collecting the data. So, when we looked at stuff the other day, we may have had something where they said X and Y, and they told us X was 2, and where X was 2, the Y was 7. So our X sub I here is 2. That's the original data X that we were given, and the Y sub I is 7. Those are just the original ordered pairs that you're given, the original X's and Y's that were in the data. X bar is the mean of the X values. So if you added up all the X values that you have in your data and divided it by how many of them there are, that's what X bar is. Y bar is the mean of all the Y values in the data. Remember, one thing we said about the regression line is every regression line, every line of best fit, this point right here is always going to fall on that regression line. The mean of the X's and the mean of the Y's, if you graph that point, it's always going to fall on that regression line somewhere. The other key one, key symbol that we're going to use is Y hat sub I, and that Y hat sub I is the predicted Y value at a certain X, at a certain X value, X sub I. So when we're looking at this, if we're on our line here and we have some x here, let's say 5, and we're going to predict what our y comes out to be. This y value right here is your y hat sub I for your original x sub I being 5. So that's our predicted. Now that doesn't come from the actual data, because where x is 5 on the data, that point could be, somewhere below or somewhere above or anywhere else. But this is what we're predicting it, our y to be at that certain value using our regression line. So we're making that prediction using that formula that we wrote, or using the equation that we wrote for our regression line. Your total deviation is always y sub I, so all the y's minus each x or each y bar, and you have to do that for every point to find the total deviation, or how much all of them are deviating from the prediction. So that's right here. If I'm looking at this, your total deviation is, this is the actual point that we have in our data that we collected, and then this is our mean of our y's down here, and this whole thing right here is our total deviation. That's how much we're off of that, how much we're deviating from here to there. Then your explained deviation is your predicted, what y you predicted, minus the mean of your y's, and that's this part. So here's the mean of our y's, here's the y that we predicted at that point, at that x, whatever this certain x is down here. That's what we predicted. Well, that's the explained deviation. That distance from there to there, that's how much we can explain, how much of the deviation we can explain. The unexplained deviation is this part from what we predicted up to what the actual point was in the data. So it's that distance. That's the part of the deviation, that's the part that we cannot explain. You'll notice when you have this distance and this distance together give you your total your total deviation. So the unexplained deviation plus the explained deviation equals the total deviation. And what we got to do is we got to find each of these for each of our for each of our ordered pairs, each of our points or our pieces of data. And in this, just to explain this a little bit, maybe not. Go on. Total variation. Total variation is a sum of the squares of the differences between the y value of each ordered pair and the mean of the y's. So it's just this. Remember, this means sum. Each original y value minus the mean of the y's. We take that and we square each one, and then we add them all up. That's the total variation. The explained variation is the sum of the squares of the differences between each predicted y value and the mean of all the y's. So this is our, remember, y hat is our predicted value using our equation, our regression line equation. We subtract the mean of the y's. Do that for every point. Square each one of them, add them all up, That's our explained variation. The unexplained variation is the sum of the squares of the differences between the y value of each ordered pair and each corresponding predicted y value. So these are the original y values that we got from the data that we were given or that we collected. The y hat is what we predicted using our equation for our line of regression, our regression line. We take all those, subtract them, square each answer, add them all up, and that gives us the unexplained variation. The sum of the explained and the unexplained variation is always equal to the total variation. Mentioned that a minute ago, that those sums will always be equal. So if we take the unexplained and the explained and add them up, that gives us the total variation. The other thing is the explained variation, just like the name tells you, is the is a part of the variation that can be explained by the relationship between your x part of your ordered pair and your y part of your ordered pair, your data. The unexplained variation cannot be explained by the relationship between x and y due to either chance or other kinds of variables that are thrown in there, whatever it happens to be. If we're comparing height to weight, so on. There's good predictions, but there's also other variables in there, like Ebersol doesn't eat well. That's why his height to weight isn't exactly what it should be. If we were to draw a line of regret or a line of best fit for males and compare their heights to their weights. So there's other variables that go into that, or it could just be chance. Something happens that causes whatever. The coefficient of determination, again, this is our R squared. That's the ratio of explained variation to total variation. We talked about this, R squared. You can find R squared by first finding R. We can use our calculator still to find R, but we can also find R squared by finding the explained variation and dividing it by the total variation. And again, what this R squared tells us is how much of the data can be, or how much of the variation can be explained and how much can't. So R squared tells you the percentage of variation that can be explained and the percentage that is unexplained. Example here, if we had our R was 0.80, we square that and we get 0.64. That's telling us that 64% of the variation can be explained just by our relationship between our x and y's for whatever reason. And then 36% is unexplained. So there's something else, other variables or chance or whatever that causes the variation, 36% of the variation. The correlation coefficient for the gross domestic products and carbon dioxide emissions data that we calculated in one of the earlier sections, it was R is approximately 0.882. Find the coefficient of determination, that's the R squared. What does this tell you about the explained variation of the data about the regression line? And what's it tell us about the unexplained? All we're going to do is we're going to take this number right here and we're going to square it. And we come up with 0.778. And what that tells us is that if we bump the decimal over 2 places, that about 77.8% of the variation in the carbon emissions can be explained by the variation in the GDP, the gross domestic products. So what we're saying there is that 77.8% of the variation can be explained just because of the relationship between our X variable and our Y's, our X data and our Y data. About 22.2% of the variation is unexplained. It's just something that some other variable causes causes it to not be exactly right. Standard error of estimate, this is where it gets a little bit more difficult. The standard, and that's what this says, standard error of estimate on top here. The standard error of estimate is the standard deviation, so how much it deviates, of the observed Y's. That's the Y sub I, that's our Y values that we know from the data, about the predicted Y, the Y hat values for a given X value, for whatever we're given in the data, the X value. It'll make more sense here in a second. So our standard error, to find our standard error, we use this formula, and we're going to do the sum of Y sub I minus Y hat sub I. This is what we got from the data. This is what we predict from our regression line. We subtract those, each one of them, square each answer, and then we add them all up. N is the number of ordered pairs that we have in the data. We subtract off 2, so it's n minus 2 on bottom there, and we take the square root of all that. That's going to give us the standard error of estimate. Remember that this part right here, this part inside here, that is your that's your unexplained variation. Sorry, I had to make sure I was telling you right. That's the unexplained variation in our data. So we're just finding that's actually that whole top there is the unexplained variation. And what we're going to do is we're going to use a chart to do these. The closer the observed Y values are to the predicted Y values, the smaller the standard error of the estimate will be. So the closer that your Y values that you have in your data are to what you predict it to be using your equation of your regression line, then the standard error, the smaller the standard error of estimate will be. So the smaller this is, that means the closer we can actually, or the better we can actually predict what a Y value should be given a certain X. We can use this chart. If we put our X's in here, whatever our X's are, and we have Y values that we were given from our collected data, just making up numbers here, those don't mean a whole or make a whole lot of difference. If we're given this, you can find the sum of them, and once you find the sum of each one of those, you could just add them all up, find the sum of all the X's, and then you could figure out what X bar is by dividing by how many of them there are. You could do the same thing for the Y's and find out what Y bar is by dividing by how many of them there are. Are predicted, this has to come, you have to use your equation. So y hat equals mx plus b. We're going to, for each x, so x is 1, we stick it in here, and we figure out what y is. Again, remember, you can get m and b from your calculator if you plug all this into your list on your calculator. So we can find each one of those. That's just what y is predicted at that certain thing. Then we're going to take this y, 5 minus this y, and it's going to give us this answer right here. And we're going to do that. So we're going to subtract each of these all the way down through here. And that's going to give us each of these answers. Then you're going to take each of these answers and you're going to square it. And that's going to give you this answer for each one. And once we square all those, we're going to add them all up. And that's our unexplained variation. And we need that unexplained variation to be able to calculate the standard error. I added on these two. To find our standard error, we really don't need these two columns, but if we know what this is, if we know what y hat is, and we find what y bar is, then we can subtract y hat minus y bar for each one and get this answer here for each one of the things down through here. And then you take each one of those answers and you square it, and that gives you these answers. And then if we add all those up all the way down through here, that gives us our explained variation. And then if we want to find the total variation, we just add those two. And if we go back here, so we need this. That was our unexplained variation. We need that from the chart to be able to find our standard error of estimate. So we need that to put into this formula, and then once we put it into this formula, we just divide by n minus 2 and take the square root of that answer, and that's going to give us our standard error of estimate. Also, if we go back, sorry, I went the wrong direction. We probably wouldn't do this, but we could take the explained error that we found in that chart, put it over, or I'm sorry, the explained variation, put it over the total variation, and that's going to tell us what r squared is. Again, if we put all the stuff into lists on our calculator, it's going to automatically tell us what r squared, what our coefficient of determination is. So we probably wouldn't do it this way, but we could. Need to find a better way to get through all this and go back and forth. So that's the chart. We're going to use that chart. Again, the last two, maybe you really don't need them, but it's not that hard to do once you've done the other 5 columns in the chart. Another method of finding the standard error of estimate is to use this formula. And this formula is a little easier, and if I skip ahead here for just a second, we could use this chart like we did back at the beginning when we were using, we used this chart, beginning of this chapter, to find the slope, the y-intercept, and to find our r. So if we had this chart, which wasn't a real difficult chart to do, to find r, m, and our b, if we have this chart, then we can, let's go back, we can pretty easily use this formula because that chart has the y squared in it, and we just add all those up. It has the y's in it, so we're going to add all those up, and it has x times y in it. We're going to add all those up. And if we plug all this stuff into our calculator again, we can find the b, which is your y-intercept, and you can find the m, which is your slope, and just plug those two in there, and then n again is how many are in the set, whatever it happens to be. The next thing I have here is I have several definitions of standard error of estimate. I'm just trying to give you as much of an explanation as possible to make sure that you sort of understand what it is. So any of this stuff that sticks with you, that it all means sort of the same thing, but any of it that sticks with you, that's what I was looking for, is just giving you or saying it several different ways, hoping something will stick with you. First definition, the standard error of estimate is the measure of variation of an observation made around the computed regression line. So you computed up this regression line for your set of data, whatever it was, maybe the regression line looked like that, and you're trying to decide or figure out the variation of the observations made around it. So how your data fell around it, so on, so on. You're making a measurement of how that data falls around that regression line. Maybe a little easier way to put it, it's used to check the accuracy of the predictions that you make off of your regression line or using your regression line. So if we go in here and we want to figure out, we say, all right, where x is 3, what's our y going to come out to be? This standard error of estimate predicts how accurate, or tells us how accurate that prediction is going to be. Sorry, got lost here for a second. Another one, the smaller the value of standard error of estimate, the closer the dots are to the regression line. So when we're looking at our data, whatever it is, maybe our data looks something like that, and we have our regression line going up through here. They're saying that the smaller the value of the standard error that we figure out is, then the closer these actual points of the data that we collected are to that regression line. And the better the estimate is based on the equation of the line. So it's gonna, if that standard error is smaller, then it's telling us that if we predict something off of our regression line, if we predict some point right there for some x on our regression line, then we're going to have a better estimate. Or it's going to be a pretty good estimate if our standard error is small, or the smaller it is, the better the estimate. If the standard error is 0, then there is no variation corresponding to the computed line, and the correlation will be perfect. So if our standard error comes out to be 0, that means whatever we predict for x at 7 or whatever, we know that our y is going to come out to be exactly that. Well, that usually doesn't happen unless, that only happens when it's a perfect correlation, perfect positive or perfect negative correlation. Thus, the standard error of estimate measures the accuracy of the estimated figures or the estimated points that we're coming out with. It is possible to decide the goodness, not really a good way to phrase this, but and the representativeness of the regression line. So in other words, we're deciding how good and how really representative of the data or of the entire population is our regression line. And how does it actually describe the relationship between the two variables, the x and the y, or the two whatever it is. It doesn't always have to be x and y, that's just what we use most of the time. So if we're making a table, we got to find all these different things. Use your regression line equation. We're going to have to get this from our calculator by putting the data into the list on our calculator. Calculate the sum of the squares of the differences between each observed. This is just doing the chart. Find the standard error of estimate. We're going to use the chart. The chart's going to tell us this top right here, and then we're just going to do the rest of the math by taking that number that we get from the chart, dividing it by n minus 2, and taking the square root of that, and that tells us the standard error. The regression equation for the gross domestic products and carbon dioxide emissions data as calculated in section 9.2 is, that's our equation that we got for that line when we did it. Find the standard error of estimate. I'll tell you what, I'm going to stop right here. This is going to be the first part, and we'll start at this example on the next video. So again, your assignment 6 is just to watch this video.